Hello everybody. In this and the next two lessons, we're going to deal with the rotation of rigid fabric elements in viscous flows. In particular, I'm going to talk about the application of Jeffrey's work on the rotation of rigid ellipsoids in slow flows. Slow here means the inertia effect, and thus gravity effect can be ignored. Rotation of rigid particles in viscous flows is very common and relevant in structural geology. Here we are looking at a granitic malonite from the Okanagan Valley Fault Zone from BC, Canada. You can see these porphyroclastic feldspars. They behave as rigid objects in the ductile flow. Mica fish porphyroclasts can also be regarded as rigid objects. Fine-grained micas defining this C-foliation of the malonite, and a dynamically crystallized quartz forms the matrix of the malonite. So it is important to realize that the rotation or motion in general of rigid objects in ductile flow is a three-dimensional problem, even though our observations are made on two-dimensional thin sections. Every one of these porphyroclasts is a three-dimensional object, even though they appear as a two-dimensional ellipse on this cross-section. And it's also important to realize that the motion of these porphyroclasts, these rigid objects in the ductile flow, includes both translation and rotation. As the rigid object rotates, they also translate in the flow field. Schematically shown here are spherical rigid objects. The sense of shear here is top to the right. So as the spherical objects rotate, they can also approach another particle. They can collide, and after the collision, they can form a doublet. So the two rigid objects can form a combined object and rotate with a different behavior, and eventually they can separate. So it's important that as a rigid object translates, they can change the environment nearby, and that has consequences to its rotational behavior and the development of microstructures. Rotation can lead to a shape-preferred orientation. The alignment of these porphyroclasts can define a shape fabric. In addition, another microstructure can be produced due to rigid body rotation that is related to the concept of spin or revolution of a particle. Rigid object like a garnet, as it grows, it may also be rotated, and that can lead to inclusion trail microstructures, such as something called a snowball garnet. So the snowball garnet microstructure is not produced by the reorientation of the garnet itself, but by the spinning, the angular velocity history of the garnet with respect to the rotation axis here. So that is a concept called revolution. We will talk about these different concepts later on. To describe rotation mathematically, we need to use coordinate systems. No motion will make sense until we refer that motion to a reference frame. So we use two different coordinate systems. One is the sample coordinate system, or called external coordinate system. This is the coordinate system in which the flow is defined. So we speak of the rotation of the porphyroclast in a ductile shear zone. So the ductile shear zone, the shear zone boundary, forms the external coordinate system. Because that coordinate system is regarded as being fixed, and that's a reference frame. Another coordinate system is defined by the shape of the fabric element. So if you imagine a little porphyroclastic feldspar as an ellipsoid, the three principal axes of the ellipsoid define the fabric orientation. It's a fabric coordinate system. Let us call the external coordinate system the X system, and the fabric ellipsoid fabric coordinate system the X prime system. With these two coordinate systems, we can now speak of the orientation of the fabric element in the external coordinate system. So we can speak of the orientation of x prime with respect to x. The orientation of the three-dimensional object is defined by a matrix, orientation matrix we call Q. And then the rotation of the object is really the change of Q with respect to time. Of course, you can speak of the orientation of a three-dimensional object by a set of three angles. It can be a set of three Euler angles or a set of three spherical angles. It will become very clear that it's much simpler to use Q to refer to the orientation of a three-dimensional object rather than three separate angles, because these angles are really inseparable. When we speak of the orientation of a feldspar in space, the three Euler angles defining its orientation are together. They cannot be separated because all three defines a unique orientation of the feldspar. It is much simpler to use a matrix Q to do that. It turns out that the equation for the rotation of a rigid object is remarkably simple. In the lecture notes, I give detailed derivation how we get to this equation. A very quick derivation to show you how this equation is arrived is given here in this slide and the next slide. First of all, I want to review the concept of angular velocity. A rigid object rotates, and the rotation is described by an angular velocity. It has a rotation axis, which is the orientation of the angular velocity vector. The magnitude of the angular velocity defines the angular speed of the angular rotation. The linear velocity at any point of the rigid object is going to be related to the position of that point and the angular velocity. So mathematically, it's the angular velocity cross product, the position of that point. When this relationship is expanded, the relationship is like this. It is far more convenient to write this relationship as a matrix multiplication. So instead of this cross multiplication, it's simpler to use a matrix multiplication. And instead of speaking of angular velocity vector, we speak of an angular velocity matrix or tensor. The matrix format or tensor format of the angular velocity is always such that the matrix is antisymmetric. The diagonal terms are all zero, and the off-diagonal terms are antisymmetric, which means there are only three independent components, omega 1, omega 2, and omega 3. The remaining three components are equal in magnitude, symmetric with respect to the diagonal line, and opposite in sign. So the angular velocity matrix only has three independent components as the angular velocity vector. Okay, let us remember this equation. This will be used in the next slide. Before I get to the next slide, I want to revisit the general motion of an object. A general motion of a material has both stretching, the strain rate, and also angular velocity, that is vorticity. So the velocity field is made of both a strain rate and vorticity. So you can imagine rigid body rotation as a special case. The stretching vanishes, there is only vorticity in the flow field. And the vorticity in the flow field for the rigid body is the angular velocity. How did we get this remarkably simple differential equation for the rotation of rigid object? Recall that in session 3, if we compare the rotated state and the before rotation state, the configuration relationship is by equation 1 here. X for the current position of a particle, and capital X, the original position of that same particle. Take the time derivative of equation 1, we get the velocity of that particle. Now, we want to express capital X in terms of the current X. So using equation 1 and 2, we get to this relationship. Remember from the last slide, we have this relationship. So the velocity of a particle is its angular velocity multiplied its position vector. It's a matrix multiplication here. So these two plus equation 3, we get this relationship. Remember that Q and R are related by this relationship. Q is the transpose of R. Using this relationship, equation 4 becomes this relationship. So far, the angular velocity is expressed in terms of the external coordinates. So we're talking about the rotation with respect to an external coordinates. It is more convenient to express the angular velocity in terms of the current coordinate, that is the coordinate of the fabric itself. And the relationship is expressed by this tensor transformation. And when we combine these two, we get the final equation. So this is the equation. Okay, chapter 9 of the lecture notes gives more details on how we get this equation. So now we have this mathematical equation to describe the rotation. We need to solve this equation in order to know the history of a rigid body rotation. So the angular velocity of a rigid object in a ductile flow is a complicated function. It depends on the flow itself, depends on the current orientation of the object, and also depends on the geometrical characteristics of the object, of course. This year is the 100 years anniversary of the publication of the celebrated work of G.B. Jeffrey, and we are going to use Jeffrey's expression for the angular velocity to investigate the rotational behavior of rigid ellipsoid objects in viscous flows. Angular velocity of a rigid object in viscous flows. Jeffrey's work was published 100 years ago in Proceedings of Royal Society of London. I recommend that you download a copy of this seminal paper. A significant result that we will use is the angular velocity expression. To summarize the angular velocity result from Jeffrey, it's this one. So the angular velocity, the term that occurs in the equation I just presented to you, equals to vorticity plus this term. I equal 1, 2, 3 are the three semi-axis lengths of the ellipsoid. The principal axis of the rigid ellipsoid are A1, A2, A3. Wij is the vorticity of the ductile flow in which the ellipsoid is embedded. And Dij is the strain rate of the surrounding flow field. First of all, both the strain rate and the vorticity will contribute to the angular velocity of a rigid object. If the object is a sphere, then this second term becomes 0. So we come to the conclusion that for a spherical object, the angular velocity is exactly the vorticity of the surrounding fluid. The vorticity contribution to the angular velocity is that every object must rotate at an angular velocity that is appropriate for the vorticities. The object is also affected by the strain rate part. The strain rate part will vanish if the object is spherical. It will also vanish if the object has principal axis parallel to the principal axis of the strain rate. To solve this equation analytically, it's not possible unless it's for simple situations. If the flow field is monoclinic, and also the object are spheroidal. A spheroidal object is an ellipsoid with rotational symmetry. If an object is spheroidal, then its shape can be described by just a single parameter, b. For oblate object, b is less than 0. And for a prolate object, b is greater than 0. b is uniquely related to the aspect ratio. Aspect ratio is A1 axis divided by A2 axis. Analytic solutions of the equation is possible only for the simple situations if the flow field is a monoclinic flow field. So the velocity gradient tensor can be expressed by a matrix like this. Imagine that we define the flow in the coordinate system XYZ here. Imagine a shear zone-like environment. So the shear plane is parallel to the y-axis. The strain rate parallel to x-axis, y-axis, z-axis are here. So this flow field has monoclinic symmetry. And this flow field can be simplified by using three dimensionless numbers. One is the sectional kinematic vorticity number. And the second is the sectional kinematic vorticity number divided by the shape factor, b. We call that factor lambda. And third is z, which is the strain rate along the z-axis divided by the shear strain rate. The orientation of a spheroidal object is defined by its orientation of the distinct axis. So the distinct axis has a theta angle trend and an angle phi. With this setup, the differential equation for rotation boils down to these two differential equations. One equation for theta and another equation for phi. And we can use a dimensionless time, gamma, which is a shear strain parallel to y-axis. Gamma simply equals gamma dot multiply t. So the differential equation becomes these two differential equations, and they can be solved. Just by examining these two equations, we immediately see that the object can reach a stable position for theta if this term is 0. And it can also reach a position where phi doesn't change. If phi equals 0, so this term becomes 0. Or phi equals 90 degrees, that is, if the object's distinct axis is parallel to the vorticity axis, the phi will never change. A second situation is if the distinct axis of the object is on the vorticity normal section. Phi equals 90 degrees, phi doesn't change either. A third situation is when this term is 0, then phi is also fixed. So this has consequences to whether the object will eventually reach a stable position. So there are three distinct behaviors for a rigid spheroid in monoclinic flows depending on the parameter lambda. So we can imagine lambda as the relative significance of the vorticity number with respect to the shape. Lambda square greater than 1, those objects were permanently rotating. Vorticity dominates the behavior. The second behavior is lambda square equal 1. This is the transitional situation. The third behavior is lambda squared less than 1. That is, shape is more predominant than the vorticity. So the object will reach a position that is fixed. And remember, the lambda is positive for prolate objects and negative for oblate objects. This is why we use lambda squared, so that this parameter is always positive. Let us now investigate the behaviors of spheroids in monoclinic flows in more detail. Detailed solution of the differential equation is given in the lecture notes. The important point is that we do have three different behaviors. Behavior 1 is the object will keep rotating if lambda squared is greater than 1. So in that situation, in simple shear or in plane strain general shear, prolate object will rotate periodically, and their paths are these ellipsoidal paths. If there is a stretching along the vorticity, the object can rotate, eventually reach parallelism with the vorticity axis. So the long axis of the prolate object is parallel to the vorticity. Once reaching there, it doesn't change orientation anymore. However, it still spins around the vorticity axis. So it's a stable position, but it's not a fixed position. Oblate situation, the behavior is similar except that these paths are 90-degree rotation of the prolate situation. In the literature, people call these Jeffrey orbits because they are periodic and the object turns round and around. Behavior 2 is a situation when lambda squared equals 1. That is, the vorticity and the shape come to a balance. The behavior is that the object may rotate like a material line. The distinctive axis of a prolate object rotate along a bread circle. Oblate objects again have similar paths, but it's a 90-degree rotation of prolate objects. Third behavior situation is when the shape dominates. The vorticity is less significant than the shape. For this class, they will reach a fixed stable position. The stable orientation is at the theta s angle, synthetic to the shear direction. So the relationship is here. If there is a stretching along the vorticity axis, or if there is a shortening along the vorticity axis, the rotation paths are like this spiral shape. It may either reach a stable position or continues rotating, depends on the shape. There is also a special situation if this relationship holds. The object will reach fixed position, and that fixed position is defined by its initial orientation. So to summarize, the behaviors of rigid spheroids in monoclinic flows are completely known because we have analytic solutions. Even for monoclinic flows and spheroidal objects, the rotation behavior are very, very rich. We need to understand these behaviors and the underlying physics in order to understand the natural deformation. Of course, truly spheroidal objects are rare in rock deformation. So once the objects are triaxial, or once the fluid field is not monoclinic, then the rotation paths become more complicated. And for that, we rely on numerical solutions, which is something we will talk about in the next lecture. So just to give you a head up, if we now have a simple shear flow, okay, the flow field is still a monoclinic, simple one. However, the three semi-axes are 5 to 3 to 1. Suppose its initial A1 axis is here, A2 axis is here, and A3 axis, their orientation is projected on this stereographic projection. So the starting orientation are here. Now these are the paths of the three axes in simple shear. So look at the A1 axis. It starts here, rotates in the upper hemisphere first, as strength increases from 0 to shear strength of 10. By the time its shear strength is 20, it's here. And afterwards, it's in the lower hemisphere. Strength increases, it follows this path. Eventually, it may get to the upper hemisphere again. So to summarize, rigid body rotation follows a formally simple differential equation, which for spheroids in monoclinic flows has been solved analytically. Because we have analytic solutions, we are able to investigate the rotational behavior for spheroids in monoclinic flows thoroughly. The rotation behavior is truly rich. We talk a lot about analytic solutions. The reason for that is analytic solutions allow us to thoroughly understand the rotation behavior before we get to the more uncharted land of the rotation of more complicated situations. And also, analytic solutions are really like oases in a desert. They are precious whenever we are able to obtain them because first, they allow us to have a thorough investigation of the system, so we can understand a lot of the physics by analyzing the analytical solutions. And also, analytic solutions are precious in that they can verify our numerical solutions. When we develop numerical methods to solve a system, we can always use existing analytic solutions to verify whether our numerical approach is valid and correct. So that's it for this lesson. Thank you for your attention.